The research paper examines the assumption that underpinned the development of the Internet architecture, specifically the ability of a loosely synchronous point-to-point datagram delivery service to meet the needs of all network applications. It argues that the inability of the networking community to provide a public and affordable mechanism for asynchronous point-to-multipoint applications led to the development of private overlay infrastructure, such as CDNs and cloud networks, which contradict the open data networking goals of the early Internet advocates. The paper proposes reconsidering some deeply held assumptions to resolve the contradiction between the initial goals and the monopolistic commercial imperatives of hypergiant overlay infrastructure operators. It also discusses the technical factors that made such strategies necessary, highlighting the need for in-network support for asynchronous point-to-multipoint services. The authors emphasize the importance of addressing the underlying technical factors that led to the current ICT environment, which they describe as a stovepiped communication infrastructure. The Internet's evolution from an open data network, ODN, to Internet++ has led to a paradoxical outcome, deviating from the original goals. This is attributed to technical features of the Internet architecture. The concept of stovepipes, systems with limited focus and functionality, is discussed. Stovepipes are characterized by restricted data sharing with other systems, defining vertical information conduits within a layered system. The Internet's stovepipes include storage, networking, and computation, which interact through application interfaces, causing inflexibility and inefficiency. The spanning layer, designed for interoperability among applications, is also stovepiped, offering services to applications without direct access to supporting services. This structure is seen as a limitation in achieving universal service. The community's endorsement of policies like subsidized broadband is considered insufficient to meet the goals of universal service. The summary highlights the need to reconsider early assumptions of the Internet architecture to regain momentum towards the original goals. The limitations of stovepiped spanning layers in digital infrastructure are explored, highlighting the inflexibility and inefficiency that arise when a narrow, restricted type of functionality is standardized. The Internet Protocol Suite is cited as an example, where the datagram forwarding service is encapsulated, limiting its ability to meet diverse application requirements. When a stovepiped spanning layer is adopted as a community standard, users may encounter problems combining it with other necessary resources. Moreover, if this standard constrains access to infrastructure resources, application implementers may circumvent or ignore it, as seen in the case of Internet++. The Internet is characterized as a loosely synchronous point-to-point communication service that lacks storage and processing capabilities required by many applications, such as mass media. In response, Internet++ employs two workarounds: layering violations and private infrastructure. Layering violations involve applications accessing underlying services directly, bypassing the standardized interface, which can compromise interoperability. Private infrastructure, on the other hand, involves constructing non-shared infrastructure to support specific application classes, potentially leading to significant investment and economic power that can overshadow the original stovepiped infrastructure. The fundamental disconnect between Internet and Internet++ applications is attributed to the asynchronous, point-to-multipoint requirements of popular applications, such as mass media and public utilities. The Internet provides a synchronous, point-to-point communication service, which is insufficient to meet these demands. This mismatch drives the evolution of Internet towards Internet++. The limitations of stovepiped spanning layers and the consequences of adopting them as community standards are highlighted, emphasizing the need for a more flexible and adaptable infrastructure that can accommodate diverse application requirements. The asynchronous point-to-multipoint data and service delivery in the Internet model is naturally structured around file and object distribution applications. However, due to its reliance on point-to-point datagram delivery, it decomposes into two phases: publishing and advertising a file, followed by clients initiating independent TCP sessions for synchronous communication to retrieve the file. This process, known as iterated unicast, leads to inefficiencies in both network and server resources as the system scales up, resulting in inadequate responsiveness, inability to connect, or server instability. In contrast, the Internet++ model addresses the hotspot problem by distributing files efficiently across multiple servers and using distributed unicast to reach clients. This approach, employed by content delivery networks, CDNs, reduces the average load on any server by a factor of 1 per meter, where m is the number of servers. The total unicast traffic generated remains proportional to NP, with p being the average path length from a CDN node to a client. To keep up with the explosive growth in total internet traffic, CDNs must increase the number of deployed servers, keeping the number of servers roughly proportional to the total volume of data delivered to clients and limiting the load per server. The number of server nodes deployed to support global total traffic has remained roughly constant in recent years, with the largest global CDNs increasing their server deployments from 200,000 in 2017 to 350,000 in 2022, while the total volume of data delivered to clients has grown from 122 exabytes (MO) in 2017 to 293 exabytes (MO) in 2022. The Internet was initially considered a suitable foundation for an open data network due to its demonstrated global scalability and stateless model of point-to-point datagram delivery. However, as the network grew, limitations of this core service became apparent, leading to the emergence of content delivery networks, CDNs, and cloud services. These services repurposed Internet support infrastructure, such as DNS and BGP, to provide asynchronous point-to-multipoint services. The necessity for these services arose from the fundamental requirement of network applications to provide asynchronous point-to-multipoint services, which the Internet's unicast datagram delivery could not fulfill. Early workarounds, such as FTP mirroring, involved copying files to multiple servers, which eventually evolved into CDNs and cloud networks. These networks have their own global topologies and policy mechanisms, using Internet's components as building blocks and public-facing on-ramps. CDNs route data by making higher-level choices of which replica server a client request should be directed to, requiring knowledge and management of the underlying resource topology. This involves leveraging the Internet Domain Name Service (DNS), and even controlling the underlying topology of the network. Modern CDNs access internal BGP topology information and sometimes determine the placement of servers within the Layer 2 network, shaping the topology through contractual arrangements with Internet service providers. The growth of CDNs and cloud services has led to network ossification, as the effort to scale up distributed unicast to keep up with the growth of the network required router optimizations that ossified Internet itself at the internetworking layer. This has resulted in the emergence of a private infrastructure proportional in size and greater in economic power to the Internet communication infrastructure. The deployment of Internet protocol forwarding nodes with high capacity and low latency has become necessary to support massively growing unicast traffic. The adaptation of Internet to the pressure created by iterated unicast has ruled out the adoption of more efficient solutions to the content distribution problem. The fast path implementation in hardware boosts peak performance to unattainable levels, enabling new applications like immersive telepresence. However, these applications place greater demands on backbone routers, constraining innovation and generality in services. The Internet architecture is nominally store and forward but is used as a loosely synchronous network, supporting applications like real-time video streaming and telepresence. The fast path acceleration is now necessary for making good on the assumption of low latency. The hourglass theorem predicts that strengthening the communication service comes at a cost, ruling out some possible implementation strategies and potentially widening the digital divide. The reality is that the global communication network targets a broader public than originally envisioned, with the largest and fastest growing end-user population supported by less capable wireless connectivity. High-performance services like video streaming and telepresence are in high demand by consumers in regions with the best communication infrastructure and highest disposable income, driving efforts away from less synchronous services. The commercial imperative to support real-time streaming and telepresence has become implicit in the definition of acceptable broadband service, driving up costs and network instability. The Internet, initially envisioned as an open network for universal connectivity and access, has evolved into a private ownership-driven infrastructure, prioritizing profit over user well-being and public discourse. Internet++, built upon the Internet mechanisms, has repurposed components to support an entirely different network, contradicting the original values. The broadband requirement for low latency has made universal connectivity difficult, expensive, and unlikely. Access is restricted to information and service providers who can pay and comply with rules, leading to a cartel of hypergiants controlling application provisioning. The lack of innovation in network technologies, excluding new approaches like asynchronous point-to-multipoint data delivery, further reinforces this exclusivity. The networking community's dogma, focusing on point-to-point datagram forwarding, has turned out to be false, forcing the sacrifice of open data networking's defining goals. This has resulted in an application environment that has largely abandoned the original goals in favor of expensive strategies serving commercial interests. The legacy name, Internet, obfuscates this transformation and its exclusionary nature, leaving us with seeming paradoxes and a path forward unclear. To escape this socio-technological cul-de-sac, the network research community must take responsibility for its acquiescence in workarounds that have turned out to be fatal to the goals of open data networking. Here is a combined summary of pages 15 and 16 of the research paper. The authors emphasize the importance of acknowledging the potential consequences of creating friction-free wide-area ICT or human-seeming AI, drawing an analogy with the U.S. Constitution not being a suicide pact. They stress the responsibility of scientists and engineers to fulfill their duties and not submit to entrenched orthodoxy, lest they face the consequences of their own creations. The paper provides an extensive bibliography of 24 references, covering topics such as information technology, Internet infrastructure, and the evolution of the Internet. These references span from 1931 to 2023, highlighting the author's comprehensive review of the field. The authors cite works on the principles of Internet architecture, including the importance of interoperation, open interfaces, and protocol architecture. They also reference papers on the challenges of deploying new technologies, such as IP multicast, and the need for disruptive innovation in networking. Furthermore, the authors draw attention to the growth of mobile users worldwide, with a forecast of increasing smartphone penetration globally. They cite Statista's forecast of mobile users from 2020 to 2025 and Wikipedia's list of countries by smartphone penetration. The paper concludes by referencing Jeff Huston's article, 25 Years Later, and a Wikipedia entry on, "The Constitution is not a suicide pact." The authors seem to emphasize the need for responsible innovation and acknowledgement of the potential consequences of emerging technologies, drawing parallels with the importance of responsible governance.